Fantastic.
All right.
Okay, great. Well, hello, everybody.
Thanks, Anastasia, to join us for this event today on March 4th. Welcome to the Applied AI community. Nice to have you. And the floor is yours.
Awesome. Yeah, thanks for the invitation. The topic that I'm going to be talking about is a more contemporary statistical topic called conformal prediction. So this talk that I'm giving is based on a document that I wrote with my collaborator, Stephen Bates, which is online and you can look it up. It's called The Gentle Introduction to Conformal Prediction and Distribution-Free Uncertainty Quantification. The basic topic of this talk is basically generating rigorous and finite sample confidence intervals, we really call them prediction intervals, that work for any model and any data set for free. So, you know, you have your machine learning model, it's some neural network, it's your transformer, it's your CNN. You train it however you like to output a point prediction, you know, to predict Y from X. Now, conformal prediction is a way of taking this model and without retraining it, I can give you not just a point prediction here, but also a confidence interval around that point prediction. And it's going to be guaranteed to contain the true Y value with high probability. And that's going to hold no matter what model you use and no matter what data set you use. So I'll make that more precise in a moment. Now, the distinguishing feature of the techniques that I'm going to share is that they are black box techniques. They require no special analysis of your model and no modification of your training procedure and so on. Now, the presentation that I'm going to give is tutorial style. I'm going to be sort of like writing things on my little virtual blackboard here. So, you know, let's get started. Oh, by the way, for those of you that came in more recently, feel free to just put questions in the chat or raise your hand. It's actually better for me if you raise your hand and just, I guess Patrick will unmute you and then you can jump in. I prefer that. So motivation-wise, you know, why do we care about having these intervals around our machine learning models? Well, it's because we're going to use the machine learning models to do downstream decision-making tasks. Okay, so imagine that you're a doctor and I give you this MRI of somebody's brain. And then I also give you the output of my deep learning algorithm, which took this image in and then told you what diagnosis it thinks that the patient has. Now, the question is, do you trust the neural network to make the diagnostic decision? And of course, if you've ever worked with such algorithms, the answer is no. You don't know that the neural network has been trained well. You don't know that it sort of learns the right thing. And for that reason, accuracy is not enough. You know, even if it's 80% accurate, you don't know that your patient doesn't fall in the 20%. What you really need is some sort of like instance-wise uncertainty quantification that says for this patient, I'm pretty sure that the answer is right. In fact, I'm 90% sure that the answer is, you know, one of these answers. So what we're going to do is we're going to modify that model that was given to the doctor so that it doesn't just produce its best guess. It doesn't just say, oh, the person's normal, send them home. What it says is it gives you a set of possible diagnoses. It says the person's either normal or they have a stroke. And the true diagnosis is contained in that set with 90% probability at least. So that's what I've written down here. In other words, the true diagnosis is guaranteed to be in this set of diagnoses with high probability. And what that allows the doctor to do is to rule in or rule out harmful diagnoses. So now the doctor can say, well, if there's a chance that this is a stroke, we need to make sure we do more imaging to confirm that. And in that way, you can take your model, which may not have been reliable before, but couple it with this very rigorous form of uncertainty quantification in order to make reliable and trustworthy decisions with your algorithm. Okay. Does anybody have any questions on the motivation here before I move on?
I am checking, doesn't seem so. It's
Clear.
pretty clear so far. Yeah.
Awesome. Good.
Only so far, right? We'll see.
So far. Well, you know, just let me know if that changes.
Okay. Yeah.
Okay, good. Then let's start with some concrete details here. In particular, we're going to work in the classification setting, single class classification setting, since we're sort of all familiar with it. So yeah, this translating to computing class probabilities, I'll return to this question. The goal here, let's just make things a bit more sort of mathematically concrete. The goal here is we are given these three things. We're given a calibration data set. Okay, so let me just zoom in here a little bit so you can see. The calibration data set is a sequence of data points, right? The xi part of my data point is an image. All right, you can think about it as an image. It can actually be anything. But you can, for now, think about it as an image. So it's a big long vector of pixels. And y sub I is my class. I'm doing image classification here. So this is airplane, dog, cat, bird, and so on, all the way up until k. So we have k possible classes, and we're trying to classify y from x. But we're given this calibration data set, which is i.i.d. data. And second, we're given this model. And the model I'm going to denote as pi hat sub y of x. And the reason I'm denoting it that way is because it estimates this. Its estimation target is the conditional probability of each label given the image. In other words, I give you the image. Now I ask you, what's the probability, the true probability that this image comes from a cat? Now, if the image shows you it's very clearly a cat, then the probability is 1 that it's a cat. But maybe it's unclear whether it's a cat or a bobcat. In which case you might have, different class probabilities here. Now, the model here is an estimate of the true class probabilities. So it may not be any good, but nonetheless, we have it. Now, the third thing is a new image. I give you x sub n plus 1. You can think about it as this is your testing point. And you don't have y sub n plus 1, but you're asked to predict it. So our job is to predict y sub n plus 1 from x sub n plus 1. Y sub n plus 1 is unknown. Now, what I ask you to do, the main topic of our discussion today, is not just to predict y sub n plus 1, but to predict a set of possible classes. I'm going to denote it as T of x sub n plus 1, which is a subset of your label space. Remember, this is your label space, a subset of 1 through k. And I want you to guarantee me, actually, that it contains y sub n plus 1 with high probability. Okay, so just to recap what we just did, we took x sub n plus 1, and we put it in this mysterious function t. T is a set valued function. It takes in images and it outputs a set of classes. And we want to guarantee that the true class is in that set. Now, there's a mathematical way of saying this. It's called coverage. Coverage is the probability y sub n plus 1 is in T x sub n plus 1 is greater than or equal to 1 minus alpha. So you choose alpha. If you choose alpha equal 0.1, then I'm going to try to find a prediction set T such that y sub n plus 1 has 90% chance of being in T of x sub n plus 1. Okay. Yeah, go ahead and ask any questions if you have them.
Yeah, I have maybe a stupid question, but I guess we always want to have alpha equals 0, right?
Yeah. That's right. That's correct. So alpha is like a slack parameter, right? Alpha, if you set alpha equals 0, what happens is that you except in very rare and unrealistic circumstances, for example, if all of your model's mass is supported only on one class, then this T, in order to achieve 100% coverage, is going to have to take the entire label space.
Yeah.
So in that case, we can always ensure that this is true with probability 1 if we say probability y sub n plus 1 is in script y. Right, because script y is all classes 1 through k. But by increasing alpha a little bit, if you make alpha equal to 0.1, then maybe you can make T sub x of n plus 1 actually only include one class or two classes. And then it becomes actually useful for you as a decision-making output. Does that answer your question, Patrick?
Yeah. Alexander wants to ask a question.
Yeah, go ahead, please.
Great, thank you so much. So as I understand, we are talking about like real probabilities as opposed to, let's say, computing p-values, that is like a theoretical construct and so on. We are just talking about the probability of having a true label in the set, which is produced by this function t. Is that correct?
This is a probability. It's a marginal probability. Yeah, I mean, this does in fact hold in practice. I'm not sure what you mean by p-values being theoretical constructs. We can also compute p-values in practice.
Yeah, for sure. But I was just trying to clarify if this is like a direct probability, because like p-value would be a probability that something given a null hypothesis and so on and so on, right? So I'm just making sure if I understand this.
All probabilities are somehow thought experiments in this way. All probabilities only hold under some frame of reference. So the frame of reference here is that y sub n, like x sub n plus 1, y sub n plus 1, that data point is i.i.d. with the rest of the data points that I had in my calibration data set. If that doesn't hold, then this probability is meaningless, because this probability, to be precise, is over the randomness in this new test point and also all of the randomness in my calibration data set. Now, there are ways of doing conformal prediction when your data is not i.i.d., but I'm not discussing them right now. They're a bit more refined.
Okay, great. So if I understood you correctly, it's like what you are describing today only works, or at least only works with all the guarantees that we have when x is i.i.d., right?
Yeah, when all of your data points are i.i.d. X sub n plus 1, y sub n plus 1 is i.i.d. with these points.
Yeah, great. Thank you so much.
No worries. Okay. So let's just get more familiar with this idea of prediction sets. This will help answer the other question that was in the chat. So here I've drawn 3 squirrels from ImageNet. Okay, this is an easy squirrel, a medium squirrel, and a hard squirrel. What do I mean by that? I mean, the model should have an easy time guessing that this is a squirrel. Your neural network should have an easy time guessing that this is a squirrel. And the reason is because it's seen a lot of squirrels like this. Its background makes sense. You know, most squirrels that you see are on fences or something. Its body is in full view. You know, this is just sort of a standard stock photo of the squirrel. Now, as you move this way, the squirrels get weirder. This squirrel is on some sort of gravel that does not suggest that it's a squirrel. Its head is cut off. It's got this weird thing here in the bottom. And in fact, it's not even clear that this is a squirrel. It kind of looks more like a marmot to me, as it does to the machine learning model. And so what happens is that as you go from easy to hard, your sets grow in size. Okay, so for the easy squirrel, the set is of size 1. Right? What does that mean? It means the model's almost entirely certain that this is a squirrel. But if you look at the hard squirrel, it's really uncertain, so it gives you a big set. So now you're getting a better idea of what we want here. Generally, we want smaller sets, because smaller sets mean that we have sort of more precision. But in addition, we want our sets to modulate in size based on the difficulty of the image. Okay, so just making this a bit more concrete. The first objective that we want is this coverage guarantee above. You know, that's why we're doing all this. We want an actual rigorous guarantee. The second thing we want is small size. Generally, we just want small size sets so that they're useful for us. You know, we don't want to pick the entire label space, as we were talking about with Patrick earlier. And we also want them to be adaptive, smaller for easy examples and bigger for hard examples. So those are kind of our 3 desiderata. Okay, let me answer this question in the Q&A before I move on to the algorithm. if I use conformal prediction for out-of-class images, what would the size of the set be, or what elements would be there in that set? There's no guarantee when you use it for out of class images. By that, I presume, there's some class case k+1 that you haven't observed, and I give you an image from that. It's totally unclear. It depends on what your model does. If your model's robust to that sort of thing, then the conformal procedure might be as well. There are explicit conformal procedures that try to deal with stuff like this, and I described one in the gentle intro. But yeah, the answer to this is not clear, just based on the information provided in the question. It just depends. There's no guarantee for sure. Okay. Now let's get into the algorithm here. We've done a lot of talking in generality about conformal prediction. Now I'm going to describe to you a very simple version of conformal prediction, the simplest version that I know. Maybe before I do that, I'll call out that conformal prediction was developed by Vladimir Vovk and his collaborators, his many collaborators, in the, I guess, mid-90s. And Vovk is Ukrainian. So if you can find it in your heart to support Ukraine right now, the topics given to you in this talk came to you from Chervonohrad, which is the second largest city in the western oblast of Lviv in Ukraine.
Oh, that's interesting.
Yeah. So the basic idea of conformal prediction is, if you were to just take the model's output as given, you would be wrong, because the model isn't necessarily learning anything good. It might be arbitrarily bad. But what if we, using the calibration data set that we had from before, what if we learn a rule to predict sets? In other words, what if we just sort of calibrate the model to compensate for the fact that it might be wrong in a way that gives us a rigorous probabilistic guarantee? And it turns out that you can do this. And here's the algorithm. It only has 3 steps. And I'll explain them one by one. So the first step is you get the score of the correct class. Okay, so I'm just going to mark this up here. What happens is that I take x sub n plus 1. I'm sorry, I take x sub I, one of my calibration data points. I run it through my neural network. And then what I get is softmax outputs, one softmax output per class. All right, so this is class airplane, this is class bird, cat, dog, and so on. And now what I do is I look at the score. Let's say this image was a dog. I take a look at the score of class y sub I. So what does that mean? This is the correct class, and it has a softmax score. It might not be the highest softmax score because my model might have been wrong, but nonetheless, it has a score. And that level here, that value, I'm going to call that E sub I. Okay. So E sub I is the score of the correct class. Now, because I have an entire calibration data set, I actually have a sequence of E sub i's. So I do this for every one of my calibration points, and I store all of my E sub i's. Now I have a bag of them. Does this make sense to everybody? Yeah, good. This is clear. The second thing we do is we take roughly the 10% quantile of these E sub i's. Okay, so I've written it here in like NumPy notation. This isn't actually 0.1. In fact, there's a tiny little correction that's critical to conformal prediction. But when n is bigger than like 100, it's you can basically, it's very small. So we'll talk about it in a moment, but conceptually it's irrelevant. Yeah, so maybe I can draw a picture of what this is. What we've done is we've made a histogram of the E sub i's. And then we've set, maybe I'll take this one. We've set Q hat to be like this point here. And this point here is the one such that 10% of our data points were below Q hat and 90% of them are above Q hat. Okay. So if n were infinite, what would this mean? This would mean that if I give you the neural network of x sub n plus 1, and then I asked you what score does it assign to y sub n plus 1, the true label of x sub n plus 1, the new score has 90% probability of landing here. If n were infinite, that would be true. Now n is not infinite, so we take something slightly different here. For the 10% quantile, we take something slightly lower. But forget that for a moment. Just imagine that we've done this correction and this is true. Just, I've written it in English down here. Q hat is the value such that at least 90% of examples have score above Q hat. And then the last thing you do is you form prediction sets. Okay, so we're basically done here. What we do is we take our prediction set, our t function from before, to be the set of all classes whose score exceeds Q hat when x sub n plus 1 is input. All right, so just drawing it visually, what you do is you take your neural network, you put in x sub n plus 1, and then you get a score for each class. Looks like this. You threshold those scores at Q hat. And then this becomes your prediction set. This is 2, 5, 8. In this case, in the example that we've drawn. Okay, so this prediction set here, which is thresholded always at Q hat, satisfies a kind of magical guarantee. The guarantee that it satisfies is not only do I get coverage, so the guarantee that I asked for is satisfied by this choice of T hat. I'm sorry, TQ hat. But also, it's not too conservative. So it comes with a matching upper bound that says this set doesn't unfairly inflate in size. If I have 100 data points, in other words, my coverage is between 90% and 91%, which is good because it means that I gave you the coverage that you asked for. I didn't give you sets that were too big. And this guarantee holds for any algorithm, any choice of pi hat, any data set, any level alpha, and any calibration set size. Okay, so this is the main guarantee. This is the one that makes us excited about conformal. Any questions here? We just hit the main algorithm. Is this related to Benford's law in some way? I don't think so. No, I don't think it's related to Benford's law. Benford's law is this like a law about the distribution of probabilities, right? Let me look this up. Benford's law. Yeah, right, this thing. No, it's not. It's not related to Benford's law, as far as I know. You calculate Q hat. Yeah, no, I understand. It does kind of have that flavor because you're ranking things. There's another version of conformal that looks even more similar, but they're unrelated. So you calculate Q hat from the score of all classes. I guess the answer to that is yes. These E sub i's, they were taken by running each of our calibration examples through our model and then looking at the score of the true class. and then making a histogram of those scores and slicing them off at Q hat, right? Calculating quantiles of those scores. Yeah, good. Okay. Oh, one more question. Is it sufficient to have I.i.d. E sub I sequence to achieve coverage guarantee instead of data? The answer to that, I think, is yes, actually. If you have I.i.d. scores, then yes, it's sufficient. It's just a weird assumption, right? So people don't normally make it. Okay, so didn't we choose only one class in step one? Yeah, that's right. That's right. That's correct, Omar. But that's okay because it was the special class, right? It was the true class. And so then that guaranteed us that the next true class would be above the quantile. All right, let's move here. So just to recap what we did, just zoom out. We now know the algorithm, but at a high level, what happened? At a high level, we had a heuristic notion of uncertainty that was given to us by our model. Okay? No, it's not binary classification. It's K-class classification. Maybe somebody can answer. So if somebody understands the answer to this, maybe explain it in the comments, just so that I can move on in terms of making sure that we get to the rest of the content.
Sure.
So just to recap here, we had a heuristic notion of uncertainty. What heuristic did we have? The heuristic was 1 minus the softmax score of true class. That was our heuristic notion of uncertainty. In other words, when the softmax score of the true class is large, this number is small, so we're not very uncertain. When the softmax score of the true class is small, this number is large and we're very uncertain. So 1 is high uncertainty, 0 is low uncertainty. That's our heuristic notion of uncertainty. And then we ran it through this box that we're calling conformal prediction, where we just calculated a quantile of that quantity, Q hat. And then out at the end, what we got is this rigorous form of uncertainty given by this theorem. So we got this prediction set that comes with the guarantee. And the guarantee had correct coverage for any model and any data set. Now, the beautiful thing about conformal is that it doesn't just work for this problem. You can choose any heuristic notion of uncertainty, and this will work. And it is actually that general. You can pick any number calculated from X and use it as heuristic notion of uncertainty, run it through this sort of meta algorithm that we call conformal prediction, and get rigorous uncertainty. So the general cases I've written here, you identify a heuristic notion of uncertainty, and then you calculate the score function. Score function is big when uncertain and small when certain. And then you compute this special quantile of the score function, which we're going to call the n plus 1 times 1 minus alpha over n quantile. There's a ceiling there. In other words, you pick the n plus 1 minus alpha ceiling smallest value of the calibration points. You pick this rank point, and you call that your quantile. And then you deploy this prediction set, the set of y's such that my uncertainty is lower than Q hat. This is equivalent, there's some 1 minuses to deal with, but this is equivalent to the procedure that we just talked about. And this will work for any score function, right? I'm not going to go through the proof. I have a visual proof, but it's not too important. Basically, the reason why this works is because the scores are I.i.d, as we were talking about earlier. Now, I'm a little torn what to do with the next 25 minutes. One thing that I could do is I could just talk to you guys about different versions of conformal. But another thing that I'm thinking about is maybe we should just go into some more advanced techniques, because they're more applicable to certain industry problems like object detection or multi-class classification or outlier detection and so on. What do you guys think? You guys want to go deep into this, or do you guys want to get a little bit more of a survey of other things in the area? Non-i.i.d. Let's see. Okay. Time series, non-i.i.d. and time series. Okay, so I don't have slides prepared on these things, but perhaps I can explain them in the last like 10 minutes. I will just have to draw some pictures for you, but this can be sort of like unstructured discussion. What do you think, Patrick? For the, I'll use the, yeah, okay, survey. People want survey.
Yeah, go ahead. I mean, yeah, I just have one question, but we can take it at the end, right? So,
Fine, you could ask the question now. That was a good time.
Because, okay, and previously, okay, we were expecting one prediction, and then if I imagine it's embedded into an application or whatever, a prediction, a fault detection, whatever, right? That's fine. I take the result. It might be right, might be wrong. Now, if I have a set, how do I manage, multiple predictions, right? It's become more difficult to really integrate such results in business applications.
Yeah, good question. I mean, it really depends on your application domain. So you can imagine, like, if you are the doctor interpreting the output of the algorithm, like early on, as we discussed, then what you do is you literally look at that output and you say, my model thinks that this could be normal or stroke, and therefore I should probably investigate stroke because the consequence of missing a stroke is big.
Yeah.
But I think how to use uncertainty, people use uncertainty in, for example, control to make decisions, or in economics to sort of do to sort of trade off risk based on the size of their prediction set. So, if you're forecasting market movements, I can give you a point prediction, but actually point predictions are useless because my point prediction is like almost certainly wrong.
Yeah.
Actually, somehow interval valued estimates are the only reliable thing in all of statistics. Even calculating means. What does it mean to calculate a mean? If your data doesn't have a second moment, then you don't even have a guarantee that this thing is close to the true mean. Really, what you need is it's the interval that gave the mean its property, not the other way around. Somehow this is philosophical, right? The confidence interval tells you about the reliability of your prediction, and that's what gives your prediction its power. But more concretely, what do you do with this set as a practitioner? I think it's very application dependent, and I'm not entirely certain that I have a general answer in every case.
Well, that's fine. We need to think about it. I guess it's very use case specific, as you said, anyway. So yeah,
that makes sense. Okay, let's spend 10 minutes discussing some like extensions here. So now let's imagine we're doing like some pretty complicated problems. Like, for example, let's talk about let's talk about this. Let's talk about the setting where I give you an image of a tumor in somebody's gut, let's say, and then I'm asking you to segment that tumor, right? Asking you to do this. This is the output of like a risk control procedure, a distribution free risk control procedure that I'll describe. Now, in this setting, oftentimes it makes sense to say, I want to contain most of the tumor. I don't want my segmentation algorithm to miss more than 5% of the tumor with high probability. We're going to be able to do that for this problem using not conformal, but a technique that's similar to conformal, but better suited to these problems. Another question that you might have is, let's say I'm doing object detection. In object detection, it's a very multifaceted prediction problem. I'm asking you to identify all the objects in the image. I'm asking you to classify them, and then I'm asking you to segment them. It's called instance segmentation. So the output looks something like this. Can you give me rigorous probabilistic guarantees on this output? One of them might be coverage. For example, I'll output to you a prediction set for each object, but also a guarantee on the segmentation that the intersection over union of the segmentation is good. And also a guarantee that I've identified most of the objects that are truly in the underlying image. Let's say 90% of them. So those are three risk functions: the recall, the IOU, and the coverage. And we're going to be able to control them to make sure that all of them are within your satisfactory limits. Intuitively, the way this works is as follows. So just to return to this tumor example, because it's the easiest one. Let me just move this to the side for a second and talk about what this looks like. So intuitively, our axes here are images, and our y's are binary masks that are the same dimension as the image. And you're trying to predict y from x. And what you do is you have this model f hat, which takes xi, and it outputs 0, 1 to the height by width. So in other words, it outputs for each pixel in the image, it outputs the probability that that pixel comes from a tumor. And what you're going to do is you're going to threshold those probabilities at some level. In other words, if something is sufficiently likely to be a tumor, then you're going to color it white. And in here, by the way, my coloring scheme is that these are results, so I know the true label. White means it's a true positive, blue means it's a false positive, and red means it's a false negative. And you can see that false negatives are very rare here, because that's what we asked for in the probabilistic guarantee. Now, what I've drawn here is this thresholding procedure that I talked to you about earlier. So you can imagine this as being a slice through one of these tumor images, right? So this axis is like region in the image. It's like tissue space. And on the y-axis, I've put, and I should put a hat here, it's the estimated probability that that part of the tissue comes from a tumor, that pixel is a tumor pixel. And I'm thresholding that at level lambda, okay? So what happens if I pick lambda equals 0.7? If I pick lambda equals 0.7, then everything that's 70% or more likely to be a tumor, I'm going to color it white. I'm going to give it a +1. If I take lambda equals 0.3, then everything that's at least 30% likely to be a tumor, I'm going to give a +1. Okay, so the set with lambda equals 0.3 is larger than the set with lambda equals 0.7. There's sort of like a nesting happening here. As you turn lambda really high, I'm going to give you the null set. I'm going to give you no pixels. But if you make lambda very low, I'm going to give you the entire image. And the question is, can you pick sort of a sweet spot such that it's the smallest set that's guaranteed to contain 90% of my tumor? And the answer to that is yes. This is the false negative rate that we're going to be controlling. This is basically when this quantity is 0.1, it means that I'm containing 90% of my tumor. It's the fraction of the tumor that's contained in my set divided by the size of the tumor. I'm sorry, the number of pixels in the tumor contained in my set divided by the number of pixels in the tumor. In other words, the fraction of the tumor contained in the set, 1 minus. So notationally, what happened is that we took this false negative rate to be a risk function. Okay, so it's the expected value of a loss, where the loss is the false negative proportion. It's the fraction of missing pixels. The fraction of missing pixels is the false negative proportion. But really, this can be any risk function. So you can pick any notion of error, and you can control it in the following way. What we desire is we'd like to know the settings of lambda, all the possible settings of lambda that take our risk below the level alpha. So we choose a level for a risk, let's say 0.1, we want 90% of our tumor contained. What we'd like is to know all of the settings of our threshold that support that error level. Now, if we pick a lambda that lies in the set that actually controls the risk, we call this controlling the risk, then we're going to call T sub lambda, which is our set of pixels, a risk controlling prediction set. Risk controlling prediction set. It controls the risk with probability 1 minus delta. In other words, you violate the risk with no more than probability delta. So I usually ask the audience this question. We don't, we're running a little short on time, and I want to get to this non-i.i.d. time series stuff. So I'm going to rush through a little bit, but what's happening is that, the naive way to do this is to just take the empirical mean of your loss function. So this is sort of your empirical risk. That's what we call this. You take your loss function like the false negative proportion. In other words, you take each tumor, you run it through your algorithm, you threshold it at level lambda for every choice of lambda, and then you calculate the fraction of pixels that are missing. And you average that over all your data points. Okay, that's your empirical risk. Your empirical risk is a noisy estimate of the true risk. It looks like this. And the question is, what if I just took my little big lambda hat here, the set of all valid thresholds? What if I took that threshold, what if I took that set to be all places where the empirical risk falls below alpha? Well, the answer is I can't do that. Doing that is wrong, and it's because there's fluctuations in this r hat function. There's statistical fluctuations in it. And we need to correct for those. And the way that we can correct for those is with concentration inequalities. And from those concentration inequalities, we derive p-values. So at a high level, what we do is we discretize the space of all thresholds. For each of them, we calculate a p-value for the null hypothesis that the risk is not controlled. Okay, so this is a little bit of a brain twister here, but for each of these lambdas, you index a null hypothesis that the risk is not controlled, and then you get a p-value for that null hypothesis using something like Hufting's inequality. And after you've done that, if your p-value is small, it gives evidence against the null hypothesis. Evidence against the null hypothesis means, hey, my risk actually is controlled. Okay, so everything with a sufficiently small p-value you reject. And there's principled ways to do this using multiple hypothesis testing, for example, Bonferroni correction. So I'm not going to go through all of the technical details here so that we have time to go through the time series stuff, which is going to take me a couple minutes to explain, simply because I've actually never explained it before. So we'll be doing it online. It's also new work. I mean, this stuff was published like maybe 6 days ago.
Wow. Yeah.
So you guys are really getting it hot off the presses.
Yeah.
So yeah. Right. So anyway, doing this real procedure gives you a whole set of threshold values that each of the thresholds in which can create a risk controlling prediction set. So this applies to a wide degree of problems. So basically any prediction problem that you have, I'll give you an image and I'll output a set of classes, for example. This might be multi-label classification. Maybe I want to guarantee you that the set of classes that I return in the multi-label case is guaranteed to contain 90% of the true classes. Well, then I set my loss to be the false negative rate. I run the procedure above, and then you get sets that look like this. They just sort of like are sets that are guaranteed to satisfy a certain level of reliability, guaranteed to contain 90% of the classes in your image with high probability. So you have a couple failures here, but they happen with only probability 10%. You can also do it for hierarchical classification. So, let's say my loss function, my risk function, is graph distance in a hierarchical space. So, I would like you to, let's say you see a new type of dog, or a dog that's like, you're really not sure what breed it is, but you're sure that it's a dog. Well, I want you to output dog. I don't want you to output something that's at a finer level of resolution than you're capable of predicting. I want the model to give me its correct resolution of confidence. If you know it's a dog, give me dog, but don't tell me that it's a Cocker Spaniel if you don't know that. So the way you do this is by defining losses in graph distance, and then indexing nested sets in graph distance and calling them by their root node. And by calibrating this properly using the procedure that I described above, you get outputs that look like this. So here, the black is, I believe, the prediction. No, the black is the true class, the blue is the prediction, and the red is the true class. I'm sorry, the red is the, wait a minute. Huh. Okay. True class, the calibrated higher resolution prediction, the interior node in the graph. And then this is the model's like top one class, which was wrong. Right, so the model was sort of not sure that this was actually a hot pot, but it was sufficiently certain that it was a dish that you could eat. And so that's what it output. The same is true for all of these. So the blue is sort of at the correct level of resolution. And it always includes the black, or at least with 90% probability will include the black. Okay. You can also do this with multiple risks. So, you can do the detection example that I've talked about above. This framework is also useful for things like selective classification, out of distribution detection, and so on, because all of those problems can be expressed as risk control problems or conditional risk control problems, where you're trying to control the fraction of, for example, outliers that you let into your prediction algorithm. Okay. So does anyone have any questions here before I talk a bit about the non-i.i.d. case?
Doesn't seem so.
Good. Okay. So let me just, I'm going to write down a few papers that if you're interested in this, you should look into. The first is conformal prediction under covariate shift. This is by Tibshirani et al. This discusses the covariate shift setting, distribution shift. Another one is so this is a paper that I'm a co-author on, and this discusses the setting where you have a distribution shift that's caused by your model. So my model decides the next point to predict, and then that induces a distribution shift. And then the third one, which is the most relevant one to your questions about time series, was published a week ago, and it's called Conformal Prediction Beyond Exchangeability. Okay, so these are the three papers that you should look at. Now, I'll just very briefly discuss my understanding of this paper. Any recommendations for spatial data? I would say to some extent this works for spatial data, but there's some nuances. This last paper is probably most relevant, but it's not going to work exactly as far as I know. So let's just think about conformal prediction for a moment. What you can think about conformal prediction is doing is saying, let's construct an empirical CDF. That looks something like this. And what this is it's sort of like the sum of indicators of each of our calibration points. Score I is less than or equal to, what is our x-axis going to be? S. Okay, so obviously as x goes to 1, all of our scores are between 0 and 1 in this case, at least. So we're going to reach 1. This is an empirical CDF. And what we do with conformal prediction is we take sort of our quantile to be the n plus 1, 1 minus alpha step on the empirical CDF. All right. So now the question is, what if I were to run a procedure that doesn't count all scores the same? That, let's say, I'm doing time series. So more recent data is more reflective of my next score than data that happened 2 years ago. Well, then maybe doing this empirical CDF isn't the right thing to do. Maybe you want to look back at some of the old points just to give you some weak notion of information, but really you want to sort of like, you know, if this is my time series, then like, I'll draw this importance, and this is series. Sort of like the importance of recent points is much higher than points that happened a long time ago. Okay. So there, in fact, is a way to do this. And the way to do this is to reweight your CDF by some sequence of weights WI. Okay. So for example, you can take the WI to be equal to, you know, gamma to the, let's say we're at time step, big T. Something like that. So exponentially decaying weights, let's say. Then what does our picture look like? Our picture looks something like this. Oops, that should be monotone. Pretend this is monotone. Okay, so our picture looks something like this. In other words, the steps have length related by their weight. So points that have more value to us because they're more recent are going to reweight the CDF, are going to like contribute more to the jumps in the CDF than points that have small weights. Okay, and then when we take the quantile, we're just going to take the quantile to be this number instead. It's a different number than we did before. It's a different number because our CDF is growing at a non-uniform rate with the number of points, right? And it turns out that if you are exchangeable, no matter what sequence of weights you choose, this choice of Q hat will provide coverage. Just to be, you know, to emphasize this point, you can choose any sequence of weights W and plug them into this, and we'll be able to provide you coverage with this Q hat, with this choice of Q hat, if your data is exchangeable. If your data is not exchangeable, then your coverage will degrade by a factor that looks something like this. And I'm doing it from memory, so forgive me if I get it a little bit wrong. So the coverage degradation is no more than something like this. You know, 1 minus alpha minus the true probability of coverage differs by no more than this. So what does this mean? This means that if I give lots of weight to a point that's very different from my new point, then I don't expect my coverage to be good. But if I have a point that's very different and I weight and I give it 0 weight, then it doesn't actually affect my coverage. And so the right thing to do, kind of, is to take Wi to be small when this is large. Exactly how small? Maybe that's not entirely clear. In fact, they don't come up with an optimal sequence of weights in this paper, so that's sort of for future work. But this is sort of how you do time series. What this paper gives you permission to do under Conformal is to reweight your data, your more recent data, more in your CDF, without sacrificing the coverage under the exchangeable case. Okay, so I hope that answers the question. That's the best answer that I know. Okay, Sankalp, do you want to ask your question live?
Oh, sorry, I didn't even realize I had the raise hand button. Sorry about that.
Oh, no worries. Okay, so Ayush has a question. Is this reweighting some sort of influence function? No, it's not. It could be, because it can be any arbitrary sequence of weights. So you get to choose the weights. That's what this algorithm is telling you. There might be an optimal choice of weights. It's not telling you the optimal choice of weights, but any choice of weights that you use is going to satisfy the properties that we talked about. It gives you coverage under the exchangeable case, and it gives you the coverage degradation depends on the distribution shift. Okay, any further questions? I know we've gone a little long here, but that was a little bit of question answering.
Mm-hmm.
Yeah, and forgive me if I got some of this wrong. Maybe I should actually look at the paper while we're here just to make sure that I wrote the correct stuff. No, this is correct, it seems. Oh. Whoa. I forgot a normalization factor. There you go. Now it's correct. No, that's not quite right yet, is it? No, it's correct. That's correct. Ta-da. Okay, so I'm happy to answer any further questions you guys have, but that's basically the presentation.
There's more comment in the chat.
Yeah, if you guys are interested in learning more about this stuff, the gentle introduction is the right place to start. I also have a YouTube video that you guys can watch. It overlaps a bit with the content that you guys saw today, but not entirely. So you guys will see some other algorithms.
Yeah, the good thing is I'm going to upload the recording, so we'll have time to go through that again.
Good.
For those that have not caught everything.
Yeah, no, I know it's kind of like, you see this stuff once, but you need to see it like 10 times before it sinks in. So.
Exactly, yeah.
Yeah, but the gentle introduction, the version that's on archive or on my website, it should really help if you want to take like a more methodical look at it. I've tried to write it in a very friendly way.
Well, that's
No worries, Ross. Thanks for joining.
yeah, thanks everybody for joining. It was very, very interesting. I need to go through a couple of times, maybe 20, but I don't know how many. But let's see. Are you done, Anastasius? Yeah, you could.
Yeah, all good.
Okay.
Up to you guys. If you guys want to stay for a couple minutes and ask questions, I would.
Yeah.
But if we're not in the mood to ask questions, then I will go eat breakfast.
Yeah. We'll have dinner here.
Good.
We'll have a dinner. That was great. That was great. Okay, somebody is asking for materials. I think that.
Like you want the slides?
Oh, yeah, maybe, yeah.
Sure. Yeah, that's fine. Yeah, I have to figure out how to send these to you, but yeah. Happy to
Now,
give
what I can do, you can also send it to me. I can upload it on LinkedIn on the AI community, page, for example, or something like that.
Fine by me. Yeah. I mean, they're already on the recording, so I'm happy to share them as a PDF as well.
Yeah, please, and then I'll upload it somewhere on LinkedIn. All right. So I upload the recording on YouTube and LinkedIn, and thanks so much. That was great. Thanks for the attendees as well.
Yeah, thanks
And
for coming, guys.
let's go to the weekend.
Thank you. Great talk, really, really clear and amazing.
Appreciate it. Appreciate it. Thanks for coming. Feel free to email me too if you guys have questions.
Okay, thank you very much, Anastasios.
Yep.
It was
thank
really
you.
fascinating here too.
Yeah.
Thanks for the invite.
And
Very honored to come.
And support to Ukraine. You're right, Ayush. Thanks.
Bye, guys.
Bye-bye.
Okay, bye bye, guys.